Today, right now, we're hearing from Jacob Stegenga from the University of Cambridge. He's going to talk to us about the perils of p-hacking and the promise of pre-analysis plans, and I'm very upset he made me say all those words in a row. Please join me in welcoming Jacob.
So thank you, and thanks, Claudine, for the invitation. And I want to note that this is a co-authored paper with my co-author, Zoe Hitzig. Zoe was a MPhil student in Cambridge last year, and we started working on this paper together, and then she made this terrible life decision to study economics in Harvard for a PhD. So this is joint work. So we're here because of the replication crisis. The basic phenomenon is that many findings in the medical and social sciences can't be replicated. There have been various explanations proposed for the cause, what the reason is for the replication crisis, and one culprit that's often cited is p-hacking. So this paper tries to give an account of not so much what p-hacking is, but when exactly p-hacking is wrong, is epistemically pernicious. But p-hacking essentially involves various kinds of techniques like trimming data, excluding some data, freely analyzing one's data in a bunch of different ways to look for a positive signal in one's data, selectively reporting one's analyses, and then tuning hypotheses or model parameters to fit your data. So it's a bit like staring up at the stars and looking hard to find patterns. Of course, one thing that's interesting is that if you look at the stars long enough and employ a bunch of analytic techniques to what you observe, you'll find some true things. Right? So some scientists employ methods that just are exactly like those methods that are sometimes denigrated as p-hacking. So for instance, Alan Franklin here has argued that some really prominent discoveries in science involved the egregious exclusion of data. Okay, so, and it's not just, of course, an academic concern, it's also a very applied concern for many scientists. So this is Amy Cuddy, famous psychologist who was at Harvard. Cuddy is most known for her work on what she called power posing, which is the idea that if you strike a really dominant, powerful pose, like she is here, that increases your sense of confidence and that other people will view you as being confident and talented. She gave a TED Talk on this idea, and it was the most viewed TED Talk in history. She wrote a New York Times bestseller. And then she was accused of p-hacking. So critics claimed that Cuddy had engaged in nefarious epistemic practices that came to be called p-hacking, and that led to for a while at least, the downfall of Cuddy's ideas and arguably her career. So some critics claim that p-hacking is more vampirical than empirical, unable to be killed by mere data. So you've got your hypothesis, you've got your pet hypothesis, and you can support your hypothesis regardless of what the data actually says, because you just massage the data and analyze the data until you get the data to say what you want. On the other hand, so this is a very highly politicized issue in the medical and social sciences. So defenders of people like Cuddy are saying those people who are accusing some of us of p-hacking are really just being bullies. And a lot of the criticisms that involve claiming that somebody's been involved in p-hacking occurs outside the standard venues for scientific communication, right? So it tends not to be responses in peer-reviewed journals, but rather it tends to be blog posts. So in response to these critics, Fiske, this very famous and important social psychologist and the PhD advisor of Cuddy, claims that these critics, these people who are raising this problem of p-hacking, are involved in methodological terrorism. So in this paper, Zoe and I ask, okay, what exactly is wrong with p-hacking? What are the conditions under which p-hacking is in fact a problem? The punchline is, as so often in life, it depends on the details. So the punchline is, p-hacking is often but not always nefarious, and we are going to give like a set of formal conditions under which p-hacking is in fact a problem. Our approach is to use tools from philosophy of science. So the guiding insight of this paper is that many of the worries that have been articulated as problems for p-hacking are just like some standard issues in philosophy of science. So we draw on some technical and formal tools in philosophy of science to articulate the formal conditions under which p-hacking is epistemically pernicious and the conditions under which it's just fine. So those tools are the predictivism debate, Bayesian confirmation theory, and model selection theory. In response to p-hacking in the social sciences, psychological sciences, and medicine, many people claim that the way to mitigate the threat of p-hacking is to pre-register your experimental and analytic plan in advance of the experiment. The problem with that is that it effectively ties the hands of experimenters. Right? So if you've planned what you're going to do in advance of an experiment and your analysis, and you really stick to that plan, then there might be true positive signals lurking in your data that you can't discover. So we use the lessons from the first part of the paper to address this alleged promise of pre-analysis plans. So in the second part of the paper, we give an account of exactly when and how pre-analysis plans are epistemically valuable. In real science, it turns out we have this kind of second-order empirical work that shows that real work in the social sciences and medicine often depart from pre-analysis plans. So for instance, there's a publication a few years ago that looked at all of the pre-analysis plans that led to publications in the world's best medical journals. And then they just assessed whether or not those plans were adhered to. And the adherence rate was something like less than 50%. That's in the very best medical journals. So real science involves departures from these plans. We want to try to make sense of that, although for purposes of this talk, we won't really have time to get into that today. Okay, so there's a handout in a few piles around the room, and it's going to help to keep track of some of the technicalia in the talk. There's a few wordy passages and a bit of formalism, and so having it in front of you might help. Does everybody have a handout? Yeah, okay. There's a few extras up here if you need one. Okay, so first, we want to just get clear on what p-hacking amounts to. What is p-hacking? The kind of p-hacking that we're going to be using as a kind of running example throughout this paper is post hoc analyses of existing data. So performing subgroup analyses on experimental data in which you've got an overall population level effect. So that's what scenario one looks like. So scenario one on the handout is just a case in which a scientist has tested some causal relation using population level data, finds no effect size for the population as a whole, but then does a bunch of stratification. So stratifies the experimental population into males and females, young and old, and then on one of those cells, in one of those stratifications, finds a positive effect size. That's all that scenario one is saying. So in the way we framed it, the stratification is young and old, male and female. Really, really simple, right? We keep it simple for purposes of the kind of technical analyses that come later in the paper. Most times there are these kind of post hoc stratifications of existing data. It's a lot more involved than this, right? You can stratify data sets in an infinite number of ways. Okay, so in scenario 1, so in this example, the question is just, does this drug lower the risk of heart attacks? And it doesn't in the population as a whole, and it doesn't in any of the stratifications except for young men, okay? So E1 is the evidence from that last analysis that shows a positive effect. And H is just this hypothesis lowers the chance of heart attacks in young men. So it's a case of kind of modest p-hacking. Scenario 2 is just like scenario 1, except the scientist specifies H in advance, and the trial just includes young men. E2 is the analysis of that evidence. The content of E2 is just exactly identical to the content of E1, same number of subjects, same effect size. So the claim that p-hacking is epistemically pernicious or that post hoc data analyses are problematic amounts to holding this view. The view is that if all else is equal, p-hacking is worse than no p-hacking. If E1 and E2 have the same content, they both provide some confirmation to the hypothesis, but E1 is a result of p-hacking while E2 is not, then, and this is just a kind of semi-formal representation using tools that philosophers of science like Bayesian confirmation theory, the confirmation of the hypothesis by E1 is less than the confirmation of the hypothesis by E2. That's just an assertion of what the underlying view is about p-hacking, what the underlying concern is about p-hacking. And so what we're doing in this paper is asking, is that the case? Is p-hack in fact true? Or what are the conditions under which p-hack is in fact true? Okay. You might think that part of the problem with what's happening in scenario 1 is that the scientist has an existing data set and then tunes the hypothesis to fit the positive signal that she finds in her analysis, right? So it looks a little bit like the scientist is accommodating her hypothesis to the existing evidence. Whereas the nice thing, or the attractive thing about scenario 2 is that the scientist specifies H in advance, predicts the evidence prior to getting the evidence, and then gathers the evidence, and it turns out that the evidence confirms the hypothesis. So if that's your intuition, if your intuition is that the badness of E1 involves accommodation, whereas the goodness of E2 involves prediction, it looks exactly like a debate that philosophers of science have been having for a long time. So philosophers of science have been arguing whether or not predicted evidence is conformationally superior to accommodated evidence. It's a big, vast literature that I don't have time to go into. You'll just have to take my word for it, that the status quo today in this literature is roughly, sometimes predicted evidence is better than accommodated evidence, but not always. That's the kind of status quo. To give you a kind of feel for the sorts of arguments that this literature uses, we'll run through a few hypothetical thought experiments. It'll just take 2 or 3 minutes, and hopefully it'll be enough to persuade you that in fact, sometimes but not always, predicted evidence is better than accommodated evidence. So consider scenario 3. It's on your handout. You toss a coin 1,000 times, it lands heads on 503 tosses, that's your evidence, E3. You then formulate a hypothesis which states this coin is fair. Compare that with scenario 4. You formulate a hypothesis, H prime, which states that this coin is fair. You toss the coin 1,000 times, it lands heads 503 times, that's your evidence E4. When you compare the extent to which the evidence confirms the hypothesis, I hope that your intuition is that the evidence in both cases confirms the hypothesis equally well. In these two scenarios, there's an accommodation prediction equality.
That depends on the fact that
Yes, exactly.
Point 6, 7, it wouldn't be.
So exactly, I'm going to come to that in just a minute. So let's contrast this with the following two scenarios. Scenario 5, Mary wins the lottery. That's the evidence in scenario 5. Then Joe says the lottery is rigged in Mary's favor. That's Joe's hypothesis. Scenario 6, Joe says the lottery is rigged in Mary's favor, and then Mary wins the lottery. So in this scenario, I hope it's intuitive to you that the evidence in scenario 5 really doesn't confirm the hypothesis at all. Right? It looks like in scenario 5, Joe just has sour grapes. It's like, oh, Mary won the lottery. Well, the lottery's got to be rigged in her favor. Right? But in scenario 6, it's really telling that Joe predicted Mary winning the lottery in advance of Mary winning the lottery. The fact that Joe had this really astonishing prediction suggests, along the lines of this comment just a moment ago, that Joe is onto something, that Joe knew something about the machinations of the lottery.
What if Joe just says that every time Mary buys a lottery ticket?
That would be a different scenario. Yeah. Okay, so this idea is that in some empirical scenarios, so to sort of sum up this series of quick thought experiments, in some empirical scenarios, predicted evidence is in fact superior to accommodated evidence, but in other empirical scenarios, it's not. So if your kind of gut reaction to this post hoc data analysis practice in scenario 1 was that that's the problem is that the scientist was accommodating the evidence rather than predicting the evidence, you can't just jump to that gut reaction in light of the fact that sometimes accommodated evidence is just fine. Okay, so what's the difference between the contrasting scenarios 3 and 4 and the contrasting scenarios 5 and 6? The idea is that Joe is onto something. Joe knew something in advance of his prediction. Okay, so think about this final thought experiment, scenario 7. Yeah,
Quick question.
sure.
So far, these examples, I don't know if it's true in your paper, considers binary outcomes.
Yeah, sure.
Less than or greater than. Do you consider degrees?
We're trying to keep this, at this point in the paper, we're trying to keep it extremely simple, yeah? Because the actual underlying issues are really complicated. Yeah? So,
Because some of these distinctions disappear if you're talking about degrees rather than absolutes.
that's right, yeah, that's right. Okay, so scenario 7 has the same look and feel as scenario 1. Nadia's got 1,000 coins in her 2 pockets. She tosses each coin once, 503 lands heads. So the coins seem fair, but she then reanalyzes her data by coin type and by pocket source. And it turns out that the nickels in her left pocket tend to land heads more often than not, and that's statistically significant. If she formulates the hypothesis, nickels from her left pocket are biased to land heads, that's just a strange kind of hypothesis. It's really hard for us to imagine any kind of mechanism by which that would be the case. So the accommodation in a scenario like scenario 7 is extremely suspect, right? Now think back to the p-hacking case in scenario 1 and the contrast between scenario 1 and scenario 2. If the scientist in scenario 2 sets out in advance to test the hypothesis that this drug lowers blood pressure in young men, that's some consideration that the scientist is onto something, right? That the scientist has some prior background knowledge that the drug, in fact, has some kind of mechanism which targets this demographic group and not others. Okay, so this appeal to the prediction accommodation debate and distinguishing some cases of pernicious accommodation from some cases of non-pernicious accommodation is somewhat intuitive, but it doesn't get us very far because it doesn't tell us exactly which cases of accommodation are fine and which cases of accommodation aren't fine. There's this principle of appealing to knowledge of background mechanisms, but that's a bit opaque. So our view is that p-hack is effectively a principle of inference. It's saying if evidence comes from p-hacked methods, then that should provide less confirming support to a hypothesis than if it didn't. And so since it's a principle of inference, we ought to be able to assess it using our most general and most prescriptive theory of inference on offer today, and that is Bayesian confirmation theory. So that's what we want to do now. So is p-hacking a problem? Yeah.
Before you go on, there is a big debate about use novelty versus temporal novelty.
Yeah, sure.
And I think you want to put your...
Sure, of course. And it's a huge literature, yeah? The prediction and accommodation debate has all sorts of subtle nuances, all sorts of distinctions, like use novelty.
So it's not that the data are known, it's whether you use them to construct the hypothesis.
Say that again?
It's not that the data are known, whether you use them to construct the hypothesis that counts.
Okay. Right, yeah. I mean, look, I'm making this really quick appeal to a really huge literature, right? So I can't possibly do service in a 45-minute talk to all of the nuances and distinctions. But I would love to have that conversation with you and think about how that applies to the argument. Yeah, yeah, sure. Okay. So, a 2-minute primer on Bayesian confirmation theory. We want to use the tools of Bayesian confirmation theory to assess this principle, p-hack. Suppose your hypothesis is some causal hypothesis like D does X, and your evidence is your evidence about H. Then philosophers measure confidence in H once you've got E as a conditional probability, the probability of H given E. So since that's a conditional probability, we can apply Bayes' theorem to it, and we get the right side of the equation. And philosophers provide interpretive content to these terms in Bayes' theorem. So this term is referred to as the likelihood, which measures the impact. One way to put it is the extent to which the hypothesis explains the evidence. This term is called the prior. It's your confidence in the hypothesis before you've got this evidence. And this term is sometimes called the expectancy, which, in my view, can be used as a measure of the reliability of the method that generated the evidence. Okay. So sometimes frequentist statisticians and philosophers, and some Bayesian philosophers, argue that, or at least claim, that Bayesian confirmation theory doesn't have the intellectual resources to model biased methods. This is a passage from a forthcoming textbook by some of the world's leading Bayesian philosophers of science. They claim, whether the data were obtained by means of a bias sampling protocol, an unbiased protocol, or no protocol at all, affects neither the posterior probability nor the Bayes factor. So they're basically saying the formalism in Bayesian confirmation theory can't be used to represent bias. And that, I think, is wrong. That, I think, is just straightforwardly wrong. It's been a kind of circulating myth among some frequentist philosophers of science that's too readily accepted. So I'm going to show you how. I'm going to show you how a Bayesian can model bias. Here is the inequality that was in p-hack, and again, that's also just on your handout. Yeah, this is on page 2 of the handout. So the inequality in p-hack can just be expanded according to Bayes' theorem. And now we ask, okay, where in there can the fact that p-hacking was a problem in scenario 1 but not scenario 2 appear? It can't be in the likelihoods, these terms, P of E2 given H or P of E1 given H, because remember, the hypotheses in both cases are the same, and the content of the evidence in both cases is the same. So the hypothesis explains the evidence equally well in both cases. And similarly, it can't be the prior, right? Because the prior is just the same in both cases, and it just falls out of this inequality. So the only way that a Bayesian can make sense of this principle, p-hack, is via the expectancies, P of E1 and P of E2. It's got to be the case that P of E1 is greater than P of E2.
Science just says that's a selection effect.
Okay, let me get there. Okay, so how can this be? How can P of E1 be greater than P of E2? On its face, it's doubly puzzling, right? So one reason why it's puzzling is that, again, the content of E1 is the same as the content of E2, described in a certain way. So if the content of E1 and the content of E2 is the same, the probabilities have got to be the same. Moreover, some of you will be familiar with the famous problem of old evidence. Clark Gleamore raised this for Bayesian confirmation theory. The idea is that once you've got evidence, the probability of that evidence is just 1. So once you've got evidence, it can't serve to change your posterior. It can't serve to do what the Bayesian says it ought to do, according to Bayesian confirmation theory. So there's two kind of puzzles about this, about how star can be true. But thankfully, a solution to this old problem of old evidence can serve as a solution to both problems. So the solution is to think about what the counterfactual probability of those terms is. So don't ask, now that you've got E1, what's the probability of E1? Now that you've got E2, what's the probability of E2? Because those probabilities are just 1. But you ask the counterfactual question, if you imagine you don't currently have that evidence, what would be the probability that you get that evidence? That's a counterfactual question. If you ask that question and you redescribe E1 in the following way, multiple subgroup analyses were performed, and in one of them, there was a positive effect. So it's no longer the case that we're describing E1 as young men benefited from this drug. Rather, we performed multiple subgroup analyses, and in one of them, there was a positive effect. Then, as statisticians are well aware, the more you sample your evidence set, the more likely it is that you're going to find a spurious false positive signal. So some statisticians have this kind of joke term that they call the law of truly large numbers, which is if you do something often enough, something outrageous is bound to happen. Right? So imagine, just to give you an example of what this evidence redescription strategy is supposed to look like. Imagine Richard is struck by lightning twice, right? Which I'm wishing was the case right now. And we ask, well, what's the probability of Richard being struck by lightning twice? I mean, being struck by lightning once is extremely rare, right? And then you have to square that to get the probability of Richard being struck by lightning twice. That probability is extremely low. But if instead we redescribe the phenomena to be described as somebody was struck by lightning twice, well, there's a lot of people on Earth, and given how frequent lightning strikes in fact are and how many people there are, the odds of somebody, the probability of somebody being struck by lightning twice is extremely high. Right? So just by redescribing the evidence, the probability, its probability has gone from really low to really high. So that's what the evidence redescription strategy is doing. So here, if we describe the evidence in scenario 1 as multiple subgroup analyses were performed, and in one of them there was a positive effect, then this is in fact the case. The probability of E1 is greater than the probability of E2, because we sampled the data multiple times. So if you sample the data multiple times, you're more likely to find you're more likely to find something. It could be a true positive or it could be a false positive. One worry about this is that it involves throwing away information. So when you redescribe the evidence this way, you've gone from a description which has content about the particular subgroup which benefited from the drug to a description which loses that information. Now, some people claim that that kind of redescription should be forbidden because it involves losing information. Note that when you describe an empirical scenario. You don't have to include all of the information, right? You don't describe the color of the scientist's socks when you describe the evidence from that scientist's experiment. So it's not the case that when you describe or redescribe evidence, you've got to include all information. Well, what information do you have to include? You have to include information which is conformationally relevant. Well, how do you know what that is? Based on background knowledge. So you know that the color of the socks of the scientist in standard cases won't bear on conformation. But precisely because we know that, well, we've got this law of truly large numbers, precisely because we have this background knowledge that the scientist in scenario 1 sampled her data multiple times. So the scientist is more likely to find a false positive and a true positive signal. Redescribing the evidence in this way, it does in fact involve a loss of information. But the question is that loss of information conformationally relevant? Based on our knowledge of the multiple samples, our answer ought to be no. So if you're persuaded by that, then this strategy is okay, and we've explained p-hack, and so we have an answer to the question, what's wrong with p-hacking? I'm going to skip this. So we've argued that some cases of p-hacking involve an increase in P of E, an increase in the expectancy. But also notice, in a really straightforward way, p-hacking entails an increase in the likelihood. Right? If you have evidence, like you have in scenario 1, and you tune your hypothesis to explain exactly that evidence, that guarantees a high likelihood. Right? So p-hacking guarantees that your likelihood will go up. Now that's not fishy. Right? This is a claim about on average, yeah? Sometimes p-hacking will lead to true positive signals in your evidence. That's roughly what an increase in P in the likelihood means. But also, it will lead to spurious false positive signals in your evidence. So because confirmation, according to the Bayesian, is sensitive to only those two terms, P of E and P of E given H, it's directly proportional to the likelihood and it's inversely proportional to the expectancy. P-hacking is only a problem when the impact on the expectancy outweighs that of the impact on the likelihood. Right? Now that's a kind of long-winded way of stating something that I hope is really intuitively clear to you. Suppose you used a biased method, but your signal that you found was just really striking. You ought to be swayed by that signal. Right? An example that I like from the history of medicine is Banting and Best's discovery that insulin could modulate the symptoms of type 1 diabetes. So the therapy for type 1 diabetes at the time was starvation therapy, which meant that kids with type 1 diabetes would just go into a coma, and by the age of 15 or 16, they would die. And Banting and Best, like the day after they discovered that they could modulate symptoms of type 1 diabetes in dogs, they just walked over to one of these coma wards and just started jabbing kids with exogenous insulin. So the study was unblinded, uncontrolled, unrandomized. Like there were no methodological checks and balances at all. But the kids started waking up out of their comas. Right? So the evidence was just so striking. So that's a case in which there's according to the strictures of contemporary evidence-based medicine, no randomization, no blinding, no controls. The method was shot through with biases, but the signal was extremely large. Okay, so according to this analysis, p-hacking is sometimes epistemically pernicious. When? Well, precisely when the impact on the expectancy outweighs the impact on the likelihood. But the upshot is that it's not always pernicious. Okay. The final approach to giving an account of the formal conditions under which p-hacking is a problem, we use model selection theory. Model selection theory is a tool that's used in science which is predicated on the idea that the predictive accuracy of a model is proportional to its fit with data and its simplicity, parsimony. This is a tool that the philosopher of science Elliot Sober has used a lot in much of his work, and we're extending this kind of sober idea in this part of the paper. So this is one of the most famous formalizations of model selection theory. This is the Akaike information criterion. There's one term that measures the fit with data of a model, and one term that measures the simplicity or parsimony of the model. The basic idea is, imagine you're in a scenario in which you want to fit a curve to existing data. You've got two variables and a scatter plot, and you want to know the best way to curve fit that scatter plot. One way would be to just draw a curve that goes through every data point. Right? So you'd have a highly complicated model, which it would have perfect fit with data, but really poor parsimony. On the other hand, you could just draw a straight line through the data. So the model would have not so great fit with data, but it would be extremely parsimonious. This measure, there's a theorem by Akaike which shows that the best model, in which best means predictively accurate, the one that you can use best for future, in future cases, is the one which maximizes fit with data and maximizes parsimony according to this metric. So we want to use the insight in model selection theory and give a description of p-hacking that allows us to show the exact conditions under which p-hacking is a problem. So we're going to rethink through scenario one. So recall that in scenario one, there were two moments of analysis. There was the analysis of the data for the population as a whole, and then there was the subgroup analyses. So in that first analysis, let's just say that there was an effect size, p. It so happened that in this case, p was 0, but what the scientist is testing is a model that there is some variable such that the effect size is equal to that variable and that variable has a value greater than 0. That's what the scientist wants to test. Right? The scientist wants to know that the drug has some positive effect size. When the scientist does the subgroup analysis, things get way more complicated. In the second analysis, there were 4 effect sizes, right? 1 for each subgroup. So just call those A, B, C, and D. So when we model, when we describe the model that the scientist is testing in this scenario, it's something like this. There's a number x1 such that x1 equals A, and there's a number x2 such that x2 equals B, there's a number x3 such that, and so on. And for at least one of those, the effect size is not equal to the effect size of the population. So that's the model that the scientist is testing in the second phase of her analysis of scenario 1. Okay. So the p-hacking of scenario 1 involves the scientist first testing this model that I'm calling M, and then testing this model that I'm calling N. So now just compare the model M to the model M and N according to model selection theory. So remember, model selection theory tells us that a good model, a model that's predictively accurate, is one which has high fit with data and is parsimonious. Okay, so model M, does it have fit with data? Not so much, actually, because in fact, the effect size was 0. The model says the effect size is greater than 0. So the model doesn't have good fit with data, but it's extremely simple. The model is parsimonious. Model N has good fit with data because by stipulation, one of the subgroup analyses in fact had a non-zero effect size. But it's extremely complicated, right? It's completely non-parsimonious. So when we compare M to M and N, M wins on the parsimony property, but loses on the fit with data or accuracy property. Okay, so that working through that example shows that some cases of p-hacking, according to model selection theory, entail that the simplicity of the model decreases, but the fit with the data increases. So, according to model selection theory, p-hacking is epistemically pernicious when the impact on simplicity more than outweighs the impact on fit with data. Okay, so according to all three approaches, all three of these sort of tools from philosophy of science, p-hacking is sometimes, but not always, epistemically pernicious. That's the punchline of that part of the paper. Okay, what about pre-analysis plans? Pre-analysis plans are meant to mitigate p-hacking. So here's a description of the kinds of things that are included in a pre-analysis plan. You're supposed to include a description of the sorts of subjects who are going to be included, what outcomes will be measured, how the measures will be performed, what kind of analyses will be performed, what kind of subgroup analyses will be employed. Do you have a pre-stated plan on how to exclude outlying data? So pre-analysis plans are supposed to be quite detailed. And once you've got the pre-analysis plan in place, you're supposed to stick to it. So pre-analysis plans effectively are meant to constrain researcher degree of freedom. They're meant to constrain the experimental and analytic freedom of scientists. Okay, so is that a good thing? Well, one obvious argument is that, yeah, it's a good thing, because we know that p-hacking is a problem, right? So if we know that p-hacking is a problem and we can block it, we should. But scientific freedom is also a good thing. P-hacking can lead to the discovery of true phenomena. Pre-analysis plans mitigate that. Okay, so which of those two views is the most persuasive? The pro argument for pre-analysis plans or the con argument for pre-analysis plans? Using the resources from the first part of the paper, we can offer an answer to that question. So the pro argument is really easily vindicated because of the work that we just went through. We've already seen that p-hacking increases the expectancy, pre-analysis plans mitigate p-hacking, so pre-analysis plans decrease the expectancy, and via Bayes' theorem, that has a positive impact on confirmation. So if you can just mitigate p-hacking, you'll have a positive impact on confirmation via the expectancy. But, okay, so I'll get to the but in just a second. Same with model selection theory. Model selection theory vindicates the use of pre-analysis plans in a similar way. So p-hacking, we've seen decreases the parsimony of models of empirical scenarios. Pre-analysis plans mitigate p-hacking. So pre-analysis plans increase the parsimony of models of empirical scenarios. And by model selection theory, that entails an increase in predictive accuracy. But conversely, we know that free exploration of data and a tuned hypothesis entails a high likelihood. And pre-analysis plans mitigate that. So pre-analysis plans decrease the likelihood. by Bayes' theorem, that decreases confirmation. Same argument for the model selection. So free exploration of data and attuned hypothesis entails a high fit with data in model selection theory. And pre-analysis plans mitigate that. So pre-analysis plans decrease fit with data in model selection theory. Okay, so then how do we bring these together? How do we resolve these arguments? Okay, so we've seen that pre-analysis plans decrease the expectancy, but they also decrease the likelihood. And according to the Bayesian, a hypothesis gets confirmation if and only if the likelihood is greater than the expectancy. So pre-analysis plans add confirmation if and only if they decrease the expectancy more than they decrease the likelihood, right? Which will be the case sometimes, but not always. Same basic idea with the model selection vindication. So pre-analysis plans increase the parsimony of data models, but they decrease the fit with data of data models. So pre-analysis plans add predictive accuracy when and only when they increase simplicity more than they decrease the likelihood, which will be the case sometimes, but not always. Okay, so to quickly wrap up, the charge of p-hacking has been a really important criticism in science in the last few years. The claim that some scientist has been p-hacking can lead to, the downfall of the reputation, like happened with Amy Cuddy. And it's a kind of go-to, it's seen as an uncontroversial problem. If somebody is p-hacking, that's seen as unequivocally wrong. One upshot of these arguments is that that's not the case, right? So the various practices that amount to p-hacking can be used for the discovery of true positive findings. Okay, I'll just close. I mean, Miriam noted this already. This is a shameless self-promotion that I just finished publishing this book, Medical Nihilism, in which some of these issues, but in much less technical ways, get discussed. And that is all. Thank you.
Two examples. One from the British Medical Journal, The Lancet. There was a study made on whether aspirin decreased the chance of a second heart attack in patients who had already had a first heart attack. And the overall study showed, yes, it did. But the editors demanded division of different partition into gender, into age, etc. And the researchers said, no, we don't have enough statistics. It will show weird things. But the editors insisted and they wanted a publication. And so they did what the editors wanted, but reserved the right for other partitions. And so they found that aspirin decreased the probability of a second heart attack for all astrological signs, unless you were Gemini or Libra.
Yeah.
Which turns. Then but a more serious one is with what's known as blind analysis in high energy physics, where you set the selection criteria for events that you will accept in your data box without looking at the data box. And this has been discussed. The question is, what happens when you open the box and there's a crazy number in there? And they say, well, look, you've got to, discuss this and maybe change the criteria as long as you're honest about it. They say this is an acceptable. It's actually in the Boboar Handbook of Blind Analysis, which I got a secret copy of. but that is a case of, yeah, if you get something crazy.
Yeah, I like that example. Yeah, thanks, Alan. Yeah, that's a persuasive. So, if I understand you correctly, what you're saying is these high-energy physicists, some of them are arguing that that number should be left in the box and not looked at, and others are saying, yeah, but what if there's a striking signal?
Well, the argument is, well, you should do this and take what you get.
Yeah.
And the consensus of the groups is, no, if you get something crazy, you've got to either discount it and look and say that you're discounting it because it's crazy.
Yeah, thanks.
And it's in one of my innumerable examples somewhere.
Yeah, okay, thank you.
I can probably give it to you.
Super.
Okay, this question may betray my lack of technical expertise, but can you show, and do you need to show, that the model selection analysis is equivalent to the Bayesian?
Yeah, that's a good question. And so the two are, at least the Akaike information criterion approach to model selection theory and the kind of standard philosopher's version of subjective Bayesian confirmation theory are going after two different things. So but I think you could build. It depends on what the hypothesis is for the Bayesian confirmation theory. So if the hypothesis is future uses of this drug, say, will work for such and such patients, then the content of the hypothesis is about predictive accuracy, and the Akaike information criterion is about predictive accuracy. Yeah. So you can get them to be about similar things, but fundamentally, this Bayesian approach is about credences in our mind, like how confident should we be in this hypothesis, whereas the Akaike approach is what is the data going to look like when we do this in the future? Yeah, but thanks. Yeah.
This is very interesting. Provoking. My worry, I cannot really follow the case of likelihood. How that's a fixed number. Normally one is that's the entailment. Specific probability is statistical. How can it go up and down?
Yeah.
It's really massive for me.
Yeah. So again, so for purposes of this talk, the Bayesian approach is a subjective Bayesian confirmation theoretic approach, right? So the likelihood won't always be 1. I mean, it'll be 1 if the hypothesis entails the evidence, right?
But you should tend to look at omissions then. If A entails E, the likelihood is 1. Bayesian require that. That's logical omissions.
Mhm.
It's part of the model. You should, I suppose, know all the logical entailments, all the colors that give the probability 1.
Sure. Yeah, but if your actual evidence isn't entailed by the hypothesis, right? So, I mean, if it is, then the likelihood is 1. I grant that.
Let's see if it's not entailed. There's some statistical.
Exactly. Then there's a distribution, and it's doesn't have to be 1.
What makes you go up or down?
Yeah. Okay. So yeah, I was. Yeah. I was quick and loose about that in this presentation. So what I'm trying to argue that on average the likelihood will be higher or lower in different empirical scenarios. So and what makes it go up or down is the extent to which the hypothesis in fact explains the evidence, or the fit between the evidence and the hypothesis. So that's what's having the impact on the higher or lower likelihood. So I didn't mean to imply that, like, for a particular hypothesis in a like a token instance, it goes up or down. So I may have spoken too quickly there. The idea is to compare on average classes in which some are p-hacked and some are not p-hacked.
Okay.
Thanks, that was a really interesting talk. I've never actually p-hacked before, partially because I wasn't even sure exactly what that entailed.
Yeah.
But it sounds to me like kind of your take-home message from the talk is that there's certain exceptional circumstances where it might be okay. And I guess I was just wondering if there was kind of a take-home, like a rule of thumb, those cases in which it might be okay. Would it be just basically that the signal is so strong that it's impossible to ignore it, and it's just shouting at you from the data? Would that be kind of a...
Yeah, so there's two parts to this question that I want to take one at a time, and I think both are worth noting, and I didn't note them in the talk. So the first is just what exactly is p-hacking? It's not like there's a textbook of scientific methodology in which there's a chapter called p-hacking, and it just lays out all the different techniques which are p-hacking. So that's one of the frustrations about the discourse surrounding p-hacking is it's articulated as criticism, but what the criticisms amount to tend to be much more specific and substantive claims about, well, they performed multiple subgroup analyses and reported some subset of them, or they tuned their model parameters to fit existing data. So it's a collection of different kinds of scientific practices that then I think had just been binned as this nefarious practice. And one of the reasons why this discourse has been so loose is because it happens more in the blogosphere than it does in published journals. Well, I think there's a paper waiting to be written, if you're a grad student here interested in these issues, to answer the question just what exactly are the kinds of things that amount to p-hacking in this discourse. And then the second part of your question was, from a practitioner's point of view, like what's the take-home message? When should p-hacking sort of be allowed or not be allowed? One of what you might take to be a kind of disappointing features of this account is that we only know whether or not the formal conditions are satisfied for any particular case once the p-hacking's been done, right? So, you've got to have the evidence, and you've got to know how big the evidence is but if it's a scenario in which you're asking whether or not p-hacking is okay, then you've got to actually have done the p-hacking. And so that's a modest feature of this kind of analysis. So you've got to actually have done the p-hacking. But once you've done the p-hacking, and you ask the question, okay, how persuaded should we be by this evidence, given that we know that it was p-hacked, then the size of the signal rule of thumb comes in. So suppose the analysts did 100 subgroup analyses from a randomized trial, and in one of them found a risk difference of 2%. Then that's one way of getting at this trade-off between the worry about false positives and the size of the signal that was coming out in the formal analysis. On the other hand, if they did 20 subgroup analyses, and in one of them there was this really huge risk difference, then that's suggestive that the signal is a true positive signal. Yeah.
Even 20, I think, is a lot, maybe 2 or 3.
I totally agree with that. And one thing that I think the model selection approach really brings forward is just how rapidly complex the models get in the model selection approach on just a very few data stratifications, right? Given how massive data stratifications can get, the model selection approach, I think, shows that exactly that you're right, that 20 might just be a lot.
Probably guaranteed with 20, right?
That's what the
p-value is, 0.05.
Yeah, exactly. So if you're going with a frequentist perspective, that's the kind of rule of thumb that they say. If your statistical significance p-value is 0.05 and you run 20 analyses, then chance alone is likely to get you one spurious false positive. Yeah.
So I had a response to I'm curious how this relates to the sort of redescription argument you give. And that's just to think sort of to get off the boat right away in the sense of, so you give me some statement of evidence. So imagine that Bill had taken the blood thinners, and then we have some statement about Bill's health as a result of taking the blood thinners. I say that statement doesn't have any evidential value in and of itself, aside from a description of the broader context in which there was some statistical test being performed. So the unit of analysis has to include that context. Just like if I try to assign a probability to an event, I'm sort of implicitly assuming some outcome space and a background with which to assign a probability. So I think of the evidence claim, so that I get off the boat right away then if I take this approach and saying E1 and E2 don't have the same context. Because they're embedded in different investigative contexts, and really the unit of analysis includes all of that. And so I think the end point is going to be very similar to your point about redescription, where I say, well, look, because of the way I've thought about the first case, E1 is actually not just a test of this particular partition, it's a test of all the different partitions, right? And so I think that's probably, again, very similar to your analysis, and then you can say there's a distinction, not because of the content of the evidence claim, and in fact, we shouldn't think of those evidence claims as having the same content, but just the investigative context is different.
Yeah, I completely agree with that. I mean, one part of the paper that I didn't go through in this talk is another sort of strategy, a Bayesian strategy to exactly represent the view that you're expressing. So one way to put it would be, look, we're not just comparing P of E1 and P of E2, but we know the background context in which E1 and E2 were generated. So the pertinent comparison is P of E1 given B1, where B1 is all the background knowledge that we know about that empirical scenario, versus P of E2 given B2, where B2 is all of the background knowledge about the method that generated E2. And so I think that's one way to represent the point that you're making. I think that, that's an effective strategy to get the Bayesian approach to make sense of the problem of p-hacking. Yeah.
Rich and
Gosh, every so often, on rare occasions, I happen to know a lot about the subject the speaker is presenting. This happens to be one of them, so it's hard to know where to start. But and I actually agree with much of what you analyze here. But there's a different perspective on that I would like to suggest that there was a different light on how often pre-analysis is going to be beneficial rather than harmful. And it has to do with the fact that most science progresses on the basis of post-hoc analysis. We observe the natural world and find interesting patterns. We find interesting and unexpected things. There's something we don't usually know when we carry out pre-analysis. And when we see data, we try to explain it. I mean, the data comes first, and then the things you can say. This is really a few rare exceptions, but most of the time, science progresses on a post-hoc basis with data coming first.
I mean, imagine Darwin following a pre-analysis plan, right? Or Newton following a pre-analysis. I mean, that's
many
just,
exactly.
exactly.
So this, in my view, means that pre-analysis is generally not going to be a useful exercise, and that harm is usually going to be worse. We're lucky if we find something unexpected and different, and then we come up with new science to explain it. And so, although I agree with the analysis, I just think that the case for pre-analysis is very weak, because it's usually not going. It's usually going to. There's many reasons I have to object to it besides that, but that's sort of one chief one.
Yeah. So I'm very sympathetic to those kinds of considerations. I mean, there are all sorts of examples in science in which pre-analysis plans would have done a lot of harm, right? So then the question is, well, why are people so obsessed with pre-analysis plans? I mean, what is it about pre-analysis plans that's giving them so much traction in economics, the social sciences, medicine, psychology? I mean, I think it would be audacious for a philosopher to stand here and say, all those people are wrong-headed, right? I think they're onto something. Yeah. Well, so, I mean, we know that p-hacking can lead to spurious false positive discoveries, right? And so pre-analysis plans are an attempt to mitigate that. So that's the favorable argument towards pre-analysis plans. And in what scientific contexts is that most salient? I mean, maybe it doesn't apply to cases in which, Maybe it applies in scenarios in which we have big data. Maybe it applies when there are motivated researcher interests, like when we're testing pharmaceuticals. Yeah. So, yeah, I mean, I'm sympathetic with all of your comments, but I think a straightforward dismissal of pre-analysis plans is going too far.
I can tell you exactly why pre-analysis plans are so attractive. They're attractive to lawyers. It's a liability issue for lawyers. It has nothing to do with science, and they're not attractive to scientists at all. They're attractive to administrators and lawyers. And for administrators and lawyers, they're a great idea. They're a simple solution to potential liability. But that doesn't help science any.
Okay, yeah. Do you mean they're attractive to lawyers in the medical context, or is that like why would it?
They're attractive to lawyers and administrators because they reduce the potential liability to experiments that don't work out or results that don't hold up or things of that nature. And so it's a method of controlling things a bit, of having more control over things.
Okay.
And one of them not having any control over anyway.
But
Well, I
okay.
think that's what it's attractive to. I mean, I think we should
Yeah,
be clear
yeah.
that I don't know any scientists who find pre-analysis an attractive idea.
Pre-analysis plans are being instituted in many different scientific, like economics,
Yes,
social sciences,
almost
psychology.
exclusively by institutional
Yeah.
people.
Yeah. So I see. So when you say lawyers, you mean like lawyers representing institutions that employ
Yeah.
scientists. I see.
Yeah,
So
the
they're
General Counsel at NIH or my university.
Right.
places like that.
Yeah.
Yes, the executive vice president of research.
I see.
They're all for pre-analysis plans.
Uh-huh.
They're pushing them because they protect them.
Yeah.
But I don't think you'll find any support from them among working scientists.
Yeah.
I'm curious so I know that in physics, whether they're typical kinds of pre-analysis plans or not, but the kinds of things that Alan was referring to were adopted by physicists, and so I'm curious whether that was driven by the lawyers or whether the physicists themselves.
I don't think so. Our university might have lawyers, but I don't think CMS, in its 2,897 members or authors, has an attorney in there. They have a constitution, though. But one of the things I wanted to suggest in the case I presented yesterday of low-mass electron-positron states, when Greenberg said, yeah, we should, at the beginning, tune our cuts, which is p-hacking, when we don't know what we're looking for, is there anything of interest? The problem was they kept it up too long. And there's no formula, there's taste and knowledge and judgment that is involved. And I don't see any way of, but then again, I don't run a big experiment group,
Yeah.
thank God.
Great. So we got Derek and then one last question now.
It's going to be a little bit different. The way I approach it, since we're here for replication crisis, is why not just replicate it? I mean, as near as I can tell, there's no justification for giving any particular study much of an evidentiary value at all. Because fundamentally, it's either going to be in some way informative or useful or
Yep.
not.
Yep.
And if it is, it's going to be replicated.
Yep. Definitely. And
So,
so
I mean, your example would be, like, what's the difference on whether you predicted it or not seems to illustrate the issue of assigning any evidentiary value in the first place.
yeah.
Because any epistemic system that assigns a greater probability or likelihood of being true something based upon someone's opinion seems problematic.
Yeah, so I completely like this suggestion. I will push back a little bit, but the basic idea is to resist the starting point that it's p-hacking itself, which is a problem, right? The problem is putting too much weight on individual reports, and so let scientists p-hack all they want, and then replicate. So see if the discovered signals in a scenario of p-hacking
In a way, yeah.
hold up.
Like fundamentally, traditional course of science has been to mess about, find stuff you think is something,
Sure.
which
Yeah,
you get by what you call p-hacking.
that's right. Yeah.
But then you test it. You don't have anything until you actually do that.
Yeah. So the one kind of context in which it might be hard to do this, although I agree with you that they ought to, is in the sort of scenario that Jim has in mind when he talks about one-off experiments. So suppose you do a big randomized trial testing whether or not some drug does blah, blah, blah. And then you do these, and you find that it doesn't in the population as a whole, but then you do a stratified analysis, and you find that in this one subgroup, the drug has a positive effect size. Your suggestion is, okay, now do another trial in which you try to replicate that finding. And that's fine with me. I think you're right. In practice, what often happens is people don't want to because it's too expensive, right? So Jim's argument is that, look, it's a huge expensive trial, and we've done it once, we're not going to do it again. Some drugs have been approved on these grounds, so subgroup analyses of trials that have been completed. But I share your view that it could be there's a compelling case to be made that they ought not be approved on those grounds.
Well, I think the interesting thing to take into account is that none of these experiments happen in a vacuum. It's not like we're simply evaluating a hunch with no prior. If you're doing an RCT, you've done a crap ton of work prior to that. And the RCT is fundamentally testing the thing that you're interested in applying it for.
Sure.
So if it does have value in that one subgroup, if you're going to market the subgroup, sure, it makes sense to do it.
Yeah.
But yeah, it's not necessarily or even seemingly conceivably a problem. It's not the point you're going to do it no matter what.
I don't think it makes sense to have this conversation without discussing the difference between an exploratory study, an analysis, and a confirmatory. Like everything you're talking about is to confirm a specific hypothesis that has already come through. So of course, people would reject that because many discoveries that have brought us to a new path have been exploratory analyses. Challenge with that being you can't quantify the amount of error in an exploratory analysis. So this is the subtype of two sort of category that should be discussed. And I think it's not a fulsome discussion of these plans if we assume that they should be applied to all contexts and situations, but I see no reason why for confirming perhaps an hypothesis that arose out of an exploratory study that anyone would have an issue adhering to the process of confirming a priorly developed hypothesis. Is that what you meant in the section we didn't get to in terms of departure? Because it's one thing to depart to confirm a hypothesis, and it's another thing to depart and clearly label an exploratory study as what it is, which is scientific discovery.
Yeah, I'm really glad that you're raising this distinction between exploratory science and confirmatory science, or exploratory experiments and confirmatory. So quite often that distinction is defended among frequentist statisticians and philosophers, where the idea is you can do a bunch of science in this exploratory phase, but then when you go about testing a hypothesis, that's when you're in the confirmatory stage. And so I think part of what's motivating your comment is that p-hacking is no problem in the exploratory stage, because we're like just exploring what's out there. But maybe it's a problem in the confirmatory stage. Bayesians, and incidentally, the worries about p-hacking have typically been articulated in the frequentist context. Bayesians tend to deny that there's much of a distinction between exploratory phases of science and confirmatory phases of science. So typically for Bayesians, like evidence is evidence, hypotheses are hypotheses, and the question is just like, what's the relationship between evidence and hypothesis? I think that Bayesians go too far precisely for some of these reasons that I was suggesting here, and for some of the reasons that have come up during the Q&A. Like Bayesians can take into account these kinds of contextual features of different sort of modes of science. Yeah, thanks.
All right, please join me in thanking Jacob.